Okay, I'm going to quickly go over the notes that we did in class today. This is for those that didn't finish copying or if you were not here. So we started out on page 4 of your notes, which is on the back of page 3. It says tangent lines at the top. First thing they did was share, and then we paired up and shared, and then we talked about it. Using this circle over here, it asks us to identify the tangent line. Remember, it is a line. We name a line using 2 points on the line and the line symbol. So over here on the picture, line LQ intersects the circle at 1 point, and by definition, a tangent intersects the circle at exactly 1 point, and that point P happens to be the point of tangency. So the correct answer is either line LQ, or it could be line LP or line PQ, as long as you only use 2 letters. For number 2, if O is the center, then line segment, there should be a line segment symbol over that, line segment PO is a radius because it starts at the center and goes to the side of the circle. Number 3 asks us to find the measure of angle QPO. So here's point Q, here's point P, and here's point O. So we're talking about this angle right here, which happens to be a right angle. So since it's a right angle, it measures 90 degrees because it is a right angle. Okay, based on that information, it says write a rule. It says a line tangent to a circle, and I know some people said that it intersects the point circle at 1 point, which is fine. But what they're wanting to do is go back to that 90-degree angle. So since it forms a 90-degree angle with the radius, then we say that it is perpendicular to the radius. So a line tangent to a circle is perpendicular to the radius at the point of tangency. Okay, the point of tangent is C, B, and P. Okay, so that's at point P. Okay. All right, then it says is the opposite, and we talked about the word converse. We learned about that during the second semester. So converse meaning if we do it backwards. So if a line is perpendicular to a radius, then it means that line is tangent to the radius. Okay, so the radius, if the radius is perpendicular to the tangent line at the point of tangency. So the answer to that question is yes. Then the next part just goes over the theorems. If a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. Then it describes over here what's going on in the picture. And then the other theorem is in a plane. If a line is perpendicular to a radius of the circle at its endpoint on the circle, which would be the point of tangency, then the line is tangent to the circle. All right, then we get over into the problems. Okay, so for problem number 1, exercise number 4, it says Amiko is riding her bike on a wet street. As the bike wheel spins, water drops are sprayed off tangent, and that's the key word, tangent, to the wheel. Amika's bike wheels have a radius, gives us the word radius, of 12 inches. Find the distance the water drops have been sprayed when they are 13 inches from the center of the wheel. Then they have the picture over here drawn for you. So it shows that here's the bicycle wheel. This would be the center of the circle, which is the center of the wheel. It said that 12 is the radius, 13 is how far it is from the center, and they've got a right angle symbol drawn here, and this is the line that's tangent. So this right here would be the point of tangency. So what I did was redraw that triangle so we could see it. So I have the center of the wheel. We know that 12 inches is the radius. We know that this point right here that's on the wheel is your point of tangency, and this is where the water's spraying. So we have 12 inches, 13 inches, and some distance that we asked to find up here. Find the distance. So we're going to go back and use what we've done before, the Pythagorean theorem. We learned about that last semester. You've also learned about it in Algebra 1. Remember, the Pythagorean theorem says a squared plus b squared equals c squared. In our right triangle, A and B are the legs. That's the part that makes up the right angle. C is the hypotenuse, and I misspelled that. I apologize. Hypotenuse. Okay, and that's represented by the side C. So in our diagram, A would be 12, B would be X, or you could reverse them, say X is B, and A and 12 is B. It doesn't matter. The one that does matter is C. C is always opposite the right angle, so 13 is C. So I plug in 12 for A, X for B, 13 for C. 12 squared, 12 times 12 is 144. 13 squared is 169. Then we want to get x squared by itself, so since this is a positive 144, I subtract 144 from both sides, and that leaves me x squared is equal to 25. The opposite of squaring a number is taking the square root, so when I take the square root of both sides, I get x equals 5, and because we're using inches, our answer is 5 inches. So the water spray droplets are 5 inches from the center of the wheel. Okay. All right, our next problem. Problem number 5. I did this for some classes. Other ones we just went ahead and did number 6. It says a line L is tangent to circle P at point A. If the length of CB equals 8 and the length of AB equals 20, find the radius. Okay, so they're wanting to know what this little part right here is. So we're going to use the same thing. The only difference, and they already have it set up for us, it says R plus 8 squared is equal to R squared plus 20 squared. Okay, now we have to deal with this r plus 8 squared, because remember, if we raise it to the second power, it means that number times itself. So it would be r plus 8 times r plus 8. So we're going to use the full method that you learned in Algebra 1, or we're supposed to learn in Algebra 1. Multiply the first numbers, the outer numbers, the inner numbers, and the last numbers. So I multiply the first ones, so that's r times r, which is r squared. Then I multiply the outer numbers, r times 8, we get 8r. Then the inner numbers, 8 times r, which is 8r. And then the last numbers, 8 times 8, which is 64. So I'll write them down since both of these were all positive. R squared plus 8r plus 8r plus 64. Then I combine like terms. Since both these have the letter r, 8r plus 8r is 16r. I bring down the r squared, the 64, the r squared, and the 20 squared. Now, if you notice, they both have an r squared. They're both positive, so when I subtract r squared, they both cancel out, leaving me 16r plus 64 is equal to 400, which is 20 times 20. So then I'm going to take this by getting rid of the 64. Since it's a plus, I'm on a minus, so I'm going to subtract 64 from both sides. So I'm left with 16r equals 336. Then, and this is multiplication, the opposite is to divide. So divide both sides by 16, I get r equals 21. So our answer is 21. Now in number 6, it's similar to number 5. The only difference is this time they ask you to find two different things. It says a green on a golf course is in the shape of a circle, and they've got that drawn for you over here. A golf ball is 8 feet from the edge of the green, so from here to here is 8 feet. And 28 feet from a point of tangency on the green as shown below. So from here to a point on the circle, which is your point of tangency, is 28 feet. What is the radius? So that's the radius right here from the cup or the hole to the side of the circle or the green. So there's your radius of the green. And how far is the golf ball from the center of this, or from the cup, which is at the center of the circle? So from the cup or the hole to the ball, which is right here. So your golf ball is right here. They want to know how far that is. Well, just like in the previous problem where they gave this part right here, using segment addition postulate, we can add the r and the 8 and get r plus 8. So we know how far it is from point P to point B. Same thing here. To find out how far it is from the cup to the golf ball, we have to add the r and the 8, so we get r plus 8 on that as well, which is what I'm showing right here. We have to add it, and that's the segment addition postulate. Okay, so we're going to use the Pythagorean theorem to find the radius and use the segment addition postulate to find the distance from the cup to the golf ball. Okay, so we have r squared on our picture here, 28 and r. are A and B. It doesn't matter which one's which. We could have said 28 was A and R was B. We're going to add them, so it doesn't matter. They're just the part that makes up the right angle. R plus 8 this time is across from the right angle, making that the hypotenuse, which is letter C. So I plug in using the Pythagorean theorem, which A squared plus B squared equals C squared. So I plug in R for A, 28 for B, and R plus 8 squared, or R plus 8 for C. So I went ahead and did 28 squared. 28 times 28 is 784. Then remember, R plus 8 to the second power means R plus 8 times R plus 8. Now, this just happens to be the same exact one from example 5, so you're going to use the full method, and that's where you get the R squared plus 8R plus 8R plus 64. So you can go back and look at number 5. We're going to combine like terms, so 8R plus 8R is 16R. Then we're going to get rid of the R squared, so because I've got one on each side, so I subtract R squared, so I'm left with 784 is equal to 16R plus 64. Then I want to get rid of the 64, so I subtract 64 from both sides, so I get 720 equals 16R. Then I divide, because that's the opposite of multiplication, and I get R is equal to 45 feet, because our units of measure is feet. Now, that gives us the length of the radius, which is the first question. The second question says, what is the distance from the cup, which is the center, to the golf ball? And remember, we had to add. We used second addition postulate. R plus 8. So 45 plus 8 equals 53 feet. The next part is, some classes got to it and some didn't, the investigation. They wanted us to look at this picture and then answer. So it says, what kind of point is point C? Well, we have outside points, we have inside points, and we have points that are on the circle. Well, C is not on the circle, like A and B. It is not inside the circle, which point P is. It's outside the circle, so we call it an exterior point, because it's outside of the circle. Okay, then it says, how can we prove that tangent line AC is congruent to tangent line BC? Well, there's two ways we can do it. We can either do it by proving the triangles are congruent, and I'm going to show you that on the next page, or we could just measure, if it was where we could do it, we could just measure the length of line segment AC and the length of BC and then see if they're equal to each other. Okay, if we can't measure, then we're going to use some of the stuff from first semester. So this is what it looks like. If I draw in the radii, which means connect A to P and B to P, and I draw a line from P to C, we end up with two triangles. We got triangle PAC and triangle BPC. Well, last semester we learned that PC would be congruent to PC because of the reflexive property. Something's always congruent to itself. We can say that AP and BP line segments are congruent because all the radii of a circle are the same length, so they're equal to each other. Then we can say we know that line segment PC is also the hypotenuse of each one because it is across from the right angle on both of those. Then we can say that line segment AP and line segment BB are the legs of the triangle, because remember, the part that makes up the right angle are called the legs. So BP and BC on this triangle, PA and AC on the other triangle. Then, once we do that, from last semester, we can say that triangle PAC and triangle BPC, which are our two triangles right here, that they're congruent to each other by HL, which is hypotenuse leg, because the hypotenuse of both triangles are congruent, and the legs of one leg of the triangles are congruent. So we had only one when we went over how to prove triangles congruent that was for right triangles, and that is the HL. Therefore, now we can say that line segment AC and line segment BC are congruent because of CPCTC, which stands for corresponding parts of congruent triangles are congruent. Now, the last thing that I'm going to go over, because we did not get to this part, and you're going to need this on Monday, is exercises 7 and 8, which contains your theorem, which was on the back of page 5, which is page 6. Okay, and the theorem says that If two segments are tangent to a circle from the same exterior point, then they are congruent. So that means that line segment CA and line segment CB are congruent because they're tangent to the same circle. All right, our questions for exercises 7 and 8 says for line segment GH and line segment GI are tangent to, and that should be circle, that should be a circle right there, circle J. Somebody put an E. Find the length of GH. So GH is 2x and GI is x plus 12. And because we have this theorem up here, I know that this is congruent to this because they're two tangents to the same point outside the circle. So x plus 12 is equal to 2x. And so when I solve, I subtract x from both sides, so I get 12 equals x. And so I'm done, but I'm not done with the problem because it says find the length of GH. GH is 2x, so we say 2 times 12 and we get 24. For the second problem, same thing. I know that x plus 10 is equal to 2x minus 1 because GI and GH both are tangent to the same circle from the point outside the circle. So I get x plus 10 is equal to 2x minus 1. I subtract x from both sides and I get 10 equals x minus 1 because 2x minus 1x is x. Then I add 1 to both sides because the opposite of subtraction is addition. So I get 11 is equal to x. Then I go back and plug it in. It says that GH is x plus 10, so I plug in 11 for x, and 11 plus 10 equals 21. And that is all for what we did for today and that you will need for Monday.